Hello everyone, welcome to the ninth lecture on Introduction to Microcontrollers. In this lecture, we are going to learn about different instruction sets which are used in microcontrollers. So let's get started. So the status register, it is a hardware register that contains information about the state of the processor, and it consists of different status flags. For example, you can see here we have 0-bit DC, which is digital carry or digital borrow with bar, and C, which is a carry or a borrow with a bar. And you see these are another two status register which I have not mentioned because in our program most of the time we have these three basic status register which are affected. But if you want to get in detail, you can refer to the data sheet, and in that you can read about all these status flags. So these status flags, they basically update, they are updated based on the operation you have to indicate certain properties of the result. So for example, in your if you use any arithmetic operation into your program, and the result is 0 in that operation, then your stated your 0-bit status will be equals to 1, or you can say the 0 flag is set because the result of the arithmetic or logic operation is 0. And if the logic operation or the arithmetic operation is not 0, then the 0-bit will be made equal to 0. And same with digital carry, and so digital carry out will be 1 if a carry out from the fourth low order bit of the result occurred, and no carry out from the fourth low order bit of the result occurred, then your digital carry is going to be 0. And similar to this, if you have any carry in your operation, then your this carry bit will be equals to 1, and if there is no carry, then your C is going to be 0. So you're going to see the effect of this status flag into some of the instruction sets which we are going to study in this lecture. Now moving on to this second slide, which talks about opcode field and abbreviation description. So if you look into the data sheet, and there is a section called instruction set summary. Under that you can find this information which talks about all these status flag. So you saw in the previous slide we had other two status flag, so which I have mentioned here. PC stands for program counter, TO is timeout bit, carry you already know, carry bit, DC is digital carry bit, Z is 0 bit, and PD is power down bit. And these opcode fields we will be using many times in our instruction sets for our programs, and we need to know what all of these stands for. So F is a register file address. So whenever you see F, it means register file address, and you can see it starts from 00 to 7F. So it has a 216-bit file register which you can use into the program. And then you have W, which is a working register. And then you have B stands for bit address within a 8-bit file register. K is a literal field, constant data or label. X is don't care location, whether 0 or 1. And then D is the destination location. If D is equals to 0, then store the data into the working register. If D is equals to 1, then store the data into the file register. And the default, if you don't put anything, like if you don't put D is equals to 0 or D is equals to 1, then the default it's going to take is 1, which means it's going to save the data into your file register. And then N is for FSR. FSR is your field status register. And as I told you that it is a 16-bit addresses that allows an addressing space with with around like 65536 locations. And then we have which is a pre-post increment decrement mode selection. So most of the time we will be using all these of them, and in rare cases you would be using this field. Now moving on to the instruction sets. So the first instruction set is AND WF, so which means do the AND operation with a working resistance with working register with a file register. So this is the syntax AND WF, and then this is F, and then comma, and D. D is you provide where you want to store your data. If your D is equals to 0, then it's going to store the data into W register, and if D is equals to 1, then it is going to store the data into the file register. So I have taken an example here, and this, if you run this operation AND WF reg, comma 0, where rg is my file register, and 0 is my D, which means I want to save my data into W register, and W is your working register. So so before you provide this instruction, I'm assuming that in my working register I have this value, which is 0x17 hexadecimal number, and in binary this is how it represents. And this reg field register, it has this value, C2 hexadecimal. C is represented like this, and 2 is like this. Now we are going to use the AND operation. You can see this is the truth table for AND gate, and we are going to perform this operation on this W register and this file register. So in W register we have this value, and in the file register we have this value. So after performing the AND operation and following this table, we will get the result, and that result is going to save into the working registers, because we have 0 here, which indicates the result should store into working register. So we have this result, 02 hexadecimal number will be stored in W register. Now what is going to be stored in the reg file register? So in this register, whatever the previous value it had, it's going to be stored into this register. Now in this case the operation is not 0, so that's why your status register is going to be is not going to be affected. It's going to be 0. Now the next instruction set is AND LW, where L is your literal number, and you want to AND the literal number with W. So you know that AND literal number could be any binary number, hexadecimal number, or it can be any constant you can use. So we are going to take an example. Here you can see this AND LW 0x15 hexadecimal number. So what does this instruction set indicates? It says that this literal number should be AND with the whatever you have in the working register. So this 0x15 is your literal number, and you see here K. This K is basically called your literal number. So this literal number we are going to AND with the working register. So before instruction, which means before execution of this this instruction set, we had this value into the working register, 0x10 hexadecimal number, and what we are going to do, we are going to AND this number with this literal number. Okay, and if you do that, then you're going to get this number. So this is your final answer after doing the AND operation. So this AND operation you can use into your program if you want to have a bit you want to set the bit in this particular order, so you can use that, or you can use any other literal number and perform this instruction set. And in this case, the instruction, the Z or the 0 bit is equals to 0 because the operation is not 0. So if it was 0, then this could have been set to 1. Now next, we have inclusive or literal number with a W. So IORLW, this is the next instruction set. And I've taken up this example IORLW REG, 1. So before the instruction, we have this value in the working register, 13 hexadecimal, and this is how it represents in the binary. And then this REG field register, it has a 91 hexadecimal number. So you can see here it's written, and we are going to perform the OR operation. So whenever you use this instruction set, you will be performing OR operation. So when you perform the OR operation, the result is going to be stored in the field register. The reason why, because we have comma 1 here, and if you do that, then the result is going to be stored in the field register. So this is the working register which is having the same value, and the result is going to be stored in the REG, which is 0x93. So this is the result which has been stored into this field register, and then 0 bit affected is 0 because the operation is non-zero. That's why 0 bit is equals to 0. And this is the truth table. You can verify if the answer is correct using this truth table. Now next, we have a sub WFB. So this states a subtract W working register from file register, which is F, with borrow. Subtract working register from file register with borrow. And this is the syntax for this particular instruction set. And operation is this. And you know that F is field register is for 16-bit. It has 16 bits, so that's why it is represented like this. And the status affected in this case is C, DC is the digital carry, and Z is your 0 bit. So I have taken this example, subtract WFB REG, comma 0. If this D is 0, that means the result is going to be stored into your into the working register. Okay, so before the instruction we have REG field register is 3. So this is a very basic example I'm taking. And after this we are going to take example for 8-bit. So this is just for 4-bit I'm taking example. So you see this is 3 0 0 1 1, and in the working register you have 0 0 1 0, which is 2 in decimal, and then you already have a carry which is equals to 1. So this is the before instruction. Now let's see what is going to happen after the instruction if you subtract this W from REG field register. Okay, so to subtract, we have to convert this working register into 2's complement. Okay, so here I have already shown if you convert it into 2's complement, then you will have this number 1110. To convert it into 2's complement, I hope you already know it. You first convert it into 1's complement, which means if I take the 1's complement for this number, it's going to be 1101. And then I'll add 1 plus 1 to the 1's complement, and whatever comes out is going to be my 2's complement. So this is my 2's complement after doing that operation. And then if you have the 2's complement, then you just have to add it to the field register value. Field register is 0011, and if you add them up, you will have 0001, which is the sum, and there will be a carry of 1. Now after instruction, your REG is going to be the same because you want to store the data into the working register, and in your working register you have this 1. So this is the same thing. And then your carry is 1, digital carry is 0, and digit carry is 0, and then in this case your 0 bit is also 0. Now another example, subtract for this same instruction set, subtract W from F with borrow. And in this example, I've taken 8-bit number, and in my file list. So let's first check this out. So sub WFB reg comma 1. So if you have 1, it means it is going to store the result into the file register. So let's see. So your register is equals to 0 cross 05 hexadecimal number, and this is in binary. And then your working register is 02 hexadecimal number, and this is the binary representation. Carry is equals to 1, and then this B bar is equals to 0, because you see the operation is going to be performed is this one, F minus W minus B bar. In previous case, we didn't have any B bar. In this case, we have, which is equals to 0. So we have to perform this operation. We have to subtract in this way. So the first thing which we are going to do is to convert the W into the 2's complement. So first step, convert W into 2's complement. So if you convert this into 2's complement, you will get 1111 1110. And then add the 2's complement of W to the reg file register. File register is this value. So I have added this value to the working register. If you add them up, you will get this. This is the sum. And there will be a carry also, and that's why I've shown here. There will be a carry of 1. So what will be the result after instruction? So after instruction, after executing this command, you will get this result. Your result is this, which is 0 cross 3, and this is going to be stored in the reg file register. And there is a carry, so that's why you have carry is equals to 1. And your working register, which is W, is going to have the same value, because we have set here as 1, so it's going to store it into the file register, and working register is going to have the same value. So this is this was the example. Now let's see another example. So in this example, we are using the same command, sub WFB reg comma 1. Now here you see the field register has now 02 hexadecimal number, and working register has 01 hexadecimal number. Carry is 0, borrow is 1. So this is the difference. In the previous one, we had 0 borrow, and here we have 1. So now in this case, if you perform this operation, this is the method which you will be using up. So step 1, convert working register into 2's complement. So 2's complement of this is going to be this number, and then add the 2's complement of W to the reg field register. So this is your W, and this is your reg field register, which is 0 cross 2 hexadecimal number. If you take the sum of these two numbers, you will get this, and there will be a carry of 1. So we have performed the operation till here, F minus W. Now we have to subtract minus B bar, and in previous cases it was 0. So whatever the result you had previously here was your final result. But not in this case, because you have borrow B bar, borrow is equals to 1. So we have to see B is 1, so which means this is the literal number. It has this. So we are going to make it into a negative number. To do that, we have to convert it into 2's complement. So 2's complement of this is this number. Okay, and then once we have the 2's complement of B bar, then we are going to add that number with this result. So reg minus W is your this result. So the same result is here, which is added to negative B bar. Okay, so answer is going to be this, and there going to be a carry of 1, and that's why carry is equals to 1. And then after instruction, so after performing this operation, carry is 1, so it's the same thing, and reg is equals to 0 cross 0 0. So we know that d is equals to 1. So if d is equals to 1, then the result should be stored into the file register. If it was 0, then the result should be stored into the working register. But since it's 1, that's why we have field this file register is equals to 0 cross 0 0. And then your W is going to have same register value which it was here. So the same value is going to be here, and then carry is equals to 1, and then your Z is equals to 1. It's going to set because your operation is 0. So for this particular case, the result is 0, and that's why in this case your status is going to be equals to 1. So if you do not understand how this operation works, then I would request you to take a pause and go step by step how each step has been performed, and then you'll be able to get like how this particular instruction set works. So this is the end of the video, and there are more instruction set which we'll be doing in the next coming lectures. So thank you so much for watching.